Hi, this is Joris de Wolf for the VIB course on experimental design, and this is a short video to remind you about the important principles that we discussed in the very first online session of this course. It was really the basic principles of experimental design, and we also made a couple of exercises. We understood from the evaluation that we sent later on that some of the exercises weren't clearly understood. At least it was not clear why we did that. So I'm going to try to explain you that once more, why it's so important to do the exercise. Okay, I'll bring up my slides and I'll take you through them. Okay, so these were the slides. It was obviously about experimental design. We had our session on 1st of April, so quite a long time ago. Not bad to refresh our minds. And we started with the question, if we want to design a good experiment, what are actually the properties of a good design? And then I came up with three important characteristics. One, a good experiment is one that answers the right question properly, and both the right question and properly are here of importance. Two, the experiment should be analyzable, of course. The data coming from them should be analyzable, and the analysis should provide you an unambiguous answer. You should be clear about the question that you asked before you started the experiment. You should have a clear answer to that. The third characteristic that we didn't discuss yet in this first session is a good experiment should be efficient, and that's going to be an important part of the later sessions to study the efficiency of experiments. Now, for the first question, the right question, or the first point, answer the right question properly, we, among others, brought up this slide where we explained about the research cycle. And obviously, the course is about design of experiments, so this part. But bringing up this research cycle, I wanted to explain that this is not an activity that stands on its own. We have to know already at the moment of designing experiment how we're gonna analyze the data, because it's gonna be that data analysis that will guide us in designing experiment. Now, why I brought this slide up in this context, it's obviously that we need to have a clear question first before we can start answering it. So these parts, the research question and the more general research question and the testable hypotheses that we generate from these ones, those are really important. If we have those ones clear, the experiment will follow in a rather easy fashion. And believe me, I have so many experiences with people that ask for my help to design experiments while they themselves don't have a clear idea on what they actually would like to test. In order to make that question clearer, I took you through this mind map where we have sort of a tick list of things that you should verify before you start designing an experiment to see if you have all the questions already answered in your head. So it's obviously about objectives, but it's also about making concrete hypotheses out of these objectives. We should be aware of the constraints. Is there any time limit? Is there any money, space limit that you will have to deal with? There's an important part on responses and expected results. We should know in advance what sort of outcome would trigger us to do the next step in our research. When would we be happy with the results? When would we be disappointed with the results? So those things you should have been thinking about upfront, and that will help you to design a good experiment, because that's the questions you would like to have an answer on. The left part of this mind map is all about knowing your topic. Do you know all you need to know about your topic before you can dive into this sort of experiment? Is it already the time to do this sort of experiment that you had in mind, if you don't know some of the important things up here? One aspect that I would like to remind you about this context is this part, because it will also come back later in the course. And here I try to explain that any research is normally situated somewhere on a research path that starts with very early on experiments, where you start to learn, where you try to understand things, where you try to prove some concepts, and therefore you often need precision and specificity. Later on in your research, you would like to apply that learning in a more general context. So you want to have a more general situation in your experiment as well. So despite the fact that it may look like you're doing experiments on the same sort of topic, with the same sort of measurement, with the same sort of units that you are observing, depending on where you are on this research path, may lead to a very different experiment. Like I said, we would like to learn you how to create good experiments rather than give you recipes for particular experiments. So the essential principles that you should know is randomization, replication, and orthogonality. I'm not going to repeat things on randomization and replication, because I think that is known to everybody. Maybe orthogonality is not such a familiar term, so I would like to repeat that once more. And explaining orthogonality is probably easiest by explaining what is not orthogonal, and therefore I had this example on a survey, so not an experiment but a survey, and you would like to observe something, and you split up your people that you observe in smokers and non-smokers, and people that get sufficient exercise and people that don't get sufficient exercise. Now, those two factors are often in reality very much correlated with each other. Smokers are getting less exercise in general. Yeah. Therefore, it will be also very difficult once in your data analysis to disentangle those two factors. And that is exactly what we would like to avoid in experiments. Good designed experiments will not have these confounded factors. And we can do that by making these factors orthogonal. Yeah. It's not easy to recognize an orthogonal experiment. Often, like this one is not orthogonal. Remember, I explained that this is an experiment about nitrogen and phosphorus fertilizers and the combination of both. It's not orthogonal because if you would like to make the comparison between the three levels of P, that would be not a fair comparison, because the lowest level of P always has to deal also with the fact that it was tested with the lowest level of N. Yeah. While these higher levels of P don't suffer from that. Yeah. There's one part of the experiment that is orthogonal, this part here, where everything is nice and square. Now, it's not because we have two replicates everywhere that's not the requirement of orthogonality, because this experiment here is also orthogonal, because again, make the comparison between the three P levels and you see they all three experience the same end conditions on average. Yeah, so that's again an orthogonal experiment. Then we changed, if I can, oh, there it is, to another concept that data are basically built up out of a signal and noise. Signal is the thing that eventually you will report, yeah, as an estimate or a prediction. Yeah, the thing that you would like to estimate. The noise will go into the standard errors and the confidence intervals. Yeah, so the uncertainty you have about the signal. We're talking here about biology, life sciences, so noise will be unavoidable. So there will be uncertainty about the estimates and the predictions that you make. Obviously, you would like to get that uncertainty as small as possible, and therefore we will have to pay attention to that noise and try to control it and to manage it. Yeah, and that's basically what you do in an experimental design. To explain that further, I brought up also this slide that the data, yeah, that comprises the total variability that you can see in your data, that will be split up in several parts. One part is the part coming from the factor or the factors, there may be more of them, for which you did the experiment for. So you hope that your factors are causing some variability. Yeah, if they wouldn't, then you would have a failed experiment, or you would have to conclude that your factor has no impact. Now it's the other part that is of importance as well. The other part that is not coming from this interesting factor can be split up, hopefully, into several parts. There's going to be variability that comes from factors that you know, that you can measure, and that you can control, but it's not the reason why you did the experiment for. So we call it an uninteresting but known factor. Yeah, there may be more of them. Yeah. The important thing is that the more of this variability you can recognize, the more, or the less this remainder is. Yeah, and this part going to be important because it's the comparison between the variability coming from this factor A compared to the unknown remaining variability. It's that comparison that you will make in an ANOVA. So the bigger that ratio, obviously, the more certain you will be about the effect of your factor. Yeah, so it's a matter of getting this one as small as possible, and therefore it's important to be able to split off the variability that comes from other factors. And that was exactly why we did these. Oh, this one little thing that I wanted to mention. One of these variance components comes normally from measurement equipment, or from measurements in general. And obviously, we would like to go for the more precise one. We prefer precise measurements over unprecise measurements, unless that goes at the cost of measuring lots of units. It may be that your measurement is so complicated, so complex, so destructive, so unethical that you're not capable of doing lots of observations. In that case, a quick and dirty measurement may actually do a much better job than a precise one. So make that decision consciously. Now, again, to illustrate this part, why it's so important to be able to split up these known sources of variability, we had this exercise, these two exercises, one about the greenhouse and one about the skincare product. And so there was no experiment at all. There was nothing to be researched yet, but I wanted to bring up the exercises already now because I think it is important to understand the context in which you do a experiment, so that you know the limitations, that you know the where the variability is coming from, even if there's no experiment yet in place. Yeah? So therefore, I had these two exercises to really let you focus on what are the constraints, what are the things that cause variability that you would like to get rid of. Yeah, we will come back to these situations, and both the greenhouse and to the skincare product, and make some experiments around them. We will really apply some things and try to find out a couple of things. But I think it's important to know upfront what your context is. To illustrate that even more, I would try to give you this example. So you coming to a course of experimental design, or you're reading a good book about experimental design, and the teacher would tell you, okay, or you would find in the book, this is your ideal experiment. It contains everything that you need. It has bathrooms, sleeping rooms, it has a kitchen, it has a garage, it has everything that you need. Yeah, so this is the ideal situation. But now assume that the real situation you have to deal with is this one. So how would you get your design in this context? I mean, you would have to do all sorts of awkward manipulations to fit that design somewhere in here. So that is not a good design in this context. Yeah. So I would like to illustrate with this stupid example that knowing your context, knowing your constraints, knowing where your variability is coming from is crucial before you start designing an experiment. You can't design you can't design an experiment without knowing your context and within that context. Yeah. And you will see that the context is often much more driving how the exercise or the experiments look like. It's much more driving it than the statistical theory behind it. Okay, that's it. We are ready to start the second session.